One method of forming an alkene is using an elimination reaction. In an elimination reaction, a leaving group and a proton are removed, forming a new pi bond. So in this example, what we've done is we've eliminated a hydrogen atom as well as this chlorine, and we've generated a new pi bond in their place. This is facilitated by the use of a base. This is very similar to nucleophilic substitution reaction. The only difference is we're using a strong base instead of a nucleophile. So in this case, again, we have a substrate with a leaving group. In place of a nucleophile, we have a base. We can simplify this, writing Lg for our leaving group, B- for our strong base, and the difference is we will have a different product than a substitution reaction. In this case, we have an alkene. How do these eliminations proceed? What's the mechanism here? Well, we can imagine a bimolecular mechanism where the base will abstract a proton. The electron density from this bond will come down and form our new pi bond and kick off our leaving group. In this case, we've got a formation of our alkene right here. The base is now protonated. It will be BH instead of just B-, and we have our leaving group with a negative charge. Again, this is a bimolecular mechanism, and this is concerted, similar to an SN2 reaction. If an SN2-like mechanism is possible, you could imagine the same thing for an SN1-like mechanism, where it is unimolecular and stepwise. So if we have the same substrate, again, what if our leaving group comes off first, similar to an SN1 reaction? In this case, we have our hydrogen here. We have formed a cation, which is unstable. It would be preferential if we could somehow bring that electron density down and make a new double bond. This again will be facilitated by some base, removing that proton, breaking the bond, and forming a new alkene bond. Again, we'll have the base being protonated, we have a conjugate acid, and our leaving group as a negative charge. This is a unimolecular mechanism because the rate depends on this first step here, only one molecule, and it's stepwise, there are two steps. So let's talk specifically about a bimolecular elimination reaction. Again, drawing the mechanism really quick, this hydroxide will abstract a proton, forming a new pi bond and kicking off the leaving group. So let's draw the products. We have our alkene, we have water, and we have a chloride ion. So let's consider the transition state for this reaction. In this case, the transition state is a little bit more complicated than our nucleophilic substitution reactions. So let's draw in the bonds that aren't changing. We've got a methyl group and that bond here. Notice the bond between the hydrogen and that carbon is dissociating. We are beginning to form a new pi bond. The bond between the carbon and the leaving group is dissociating, and our hydroxide is forming a new bond with that hydrogen. So this is a little bit more complicated. Let's draw this as a transition state, and let's draw in our partial charges. The hydroxide is donating electron density to that hydrogen, so it will be partially negative, not fully negative. The chlorine is coming off of the molecule, so this is partially negative. In these transition states, we don't have any partial positive charges because if we were to draw it here, we're actually gaining more electron density as the pi bond is formed. So our transition state in this case only has partial negative charges. So we can draw a reaction coordinate diagram for this as well, where we begin with our starting materials on the left. Draw on the products real quick. We've got water and our alkene and our chloride. The products are going to be on the bottom. Because this is a concerted mechanism, we're only going to have one transition state. That's right here. And again, that transition state is where we're beginning to see the pi bond formed and the leaving group come off, along with that proton. Unlike SN2 reactions, a larger substrate will actually speed up elimination reactions, or E2 reactions. Okay, so if we have our example here, let's draw the mechanism real quick. Hydroxide grabs this proton, forms a new double bond, kicks off the chlorine. In this case, let's take a look at our transition state. We have a new pi bond forming here. We have the chlorine coming off here, and we have our hydrogen coming off here, being attracted to the hydroxide. So in this case, if we're considering electron density, this is beginning to look like just a regular alkene with no extra substituents. Remember, that's the least stable of all of the different alkene forms. What if we add a methyl group to this? If we have a methyl group, we have the same mechanism. Notice, even though there's extra steric bulk by the leaving group, the hydroxide is actually attacking much farther away over on the left here. So it's not impeded by the presence of that methyl group. But what we're seeing here is the formation of a monosubstituted alkene, which is going to be more stable than this non-substituted alkene. Finally, if we have a tertiary substrate, again, the base will attack the hydrogen, form a new double bond, and kick off the chlorine. In this case, we're beginning to form a di-substituted alkene, which is going to be even more stable, so this reaction is even more favorable. E2 reactions are also regioselective, which means the location of the double bond depends on the base and the substrate. There are two types of products. The first is a Zaitsev product, which is considered the more substituted alkene, or the Hofmann product, which is the less substituted alkene. So let's take this example here. If we have this cyclohexane molecule and we draw in the beta hydrogens, remember the site of the leaving group is the alpha site, so we have beta site here and a beta site here. We have beta hydrogen here, and we have a beta hydrogen here. You can imagine that we can deprotonate at either of these sites, which will give us two different products. So let's draw, if we eliminate at the beta 1 position here, the leaving group will come off and will form this alkene. If we deprotonate at the beta 2 position, we would actually see the formation of a double bond down here. If we want to classify these two products, the one on the left is the Zaitsev product because it's more substituted, and the Hofmann product is less substituted, will be on the right. If you want to double check that, the leftmost product has 1, 2, 3 substituents on the alkene. This is tri-substituted. In this case, we've got 1, 2 in this alkene, so it's only di-substituted. So how do we know which one of these is formed? The more substituted alkene is going to be more stable. So, assuming the hydroxide can react just as quickly with either one of these two hydrogen sites, the beta 2 or the beta 1 site, we will get the Zaitsev product preferentially. This will be favored in the case where we have a base that can easily access either site, because we're going to make the more stable alkene. Let's take another example where we have a more sterically hindered base. In this case, we've replaced a hydrogen atom with this tert-butyl group. So this is tert butoxide. So again, let's draw in our beta hydrogens. And if we're going to do a beta elimination, we have to consider the fact that the tert butoxide is bulkier than hydroxide is, which means it's going to have a more difficult time reaching a sterically hindered proton. So in this case, it is much easier for the tert butoxide to reach this hydrogen, which doesn't have to deal with this methyl group. So the methyl group kind of blocks the tert butoxide from attacking that beta 1 site. So in this mechanism, we would attack that hydrogen, form a double bond, and kick off our chlorine. The preferential product in this case will be the Hofmann product, the less substituted alkene. In fact, this will be formed in a larger excess than the Zaitsev product, even though the Zaitsev product is more stable overall. So that's what regioselective means. We can have either product depending on what base we're using or what substrate we have. In addition to being regioselective, elimination reactions are also stereoselective, which means they're going to favor the trans stereoisomer over the cis stereoisomer. Because it's more stable, there's less steric clash. So if we take a look at this example, first we want to illustrate the two beta hydrogens. there's a beta hydrogen here, which can be eliminated, and there's also one here. If we eliminate the beta hydrogen here, we will get one product. That would be this product here, which is only mono-substituted. If we eliminate at the other site, we have two other products that we could form. We can form a cis product here, or we can form a trans product. These are both di-substituted, which means they're going to be more stable and more favorable than the mono-substituted product. That's regioselectivity. But the cis form is going to be more sterically hindered than the trans form. So, in this case, we're going to favor the trans form.